Hello, everyone. I'm very excited that you are here because today we are going to um, learn the formula Black-Scholes, and I would like to say that it is the most remarkable formula in all financial theory. Okay, so if you are ready, we will start. So you remember that we set a great aim to model the dynamic of an internal market, and it means that we would like to model risky asset, riskless asset, and to evaluate a fair price of option of any other derivative. Okay, so about a riskless asset, everything is done, and we need the formula for it. But what is about stock exchanging modeling? First, we studied the one-period binomial model, after that multi-period binomial model, and some ways, yes, and you remember the Cox-Ross-Rubinstein formula. And at the past lesson, previous lesson, we studied the American option pricing in the binomial tree because it is like other kind of option. Yes, because we suppose that the market consists of at least three components, and it is like the third component, options, derivative, and it should be a European option or American option. And today we are going to learn the Black-Scholes formula. The Black-Scholes formula, and this formula gives us the fair price for European call option for continuous time. And beside this, this formula is a base for the dynamic delta hedging, and it's very important for investors. Okay, so we start with assumption. Let T capital represent the duration of the contract in years. For example, if T is 3 months, it is like 1/4 of years. Yes. N capital is the number of equal periods between trading dates. So, for example, if T capital is 3 months, we need to compute how many days we have for trading, because there are day off, and we need subtract this days off, and compute just the number of trading periods. After that, we need can obtain dt. It is like the duration in years divided by number of equals period. The next is R. R capital in this framework denotes the continuously compounded annualized interest rate. But R little is interest rate for one period. Yes, it is like we have multi-period binomial tree. We can have R little for one period and R capital for 1 year. And what is about a relationship between this? So R little, it is like R capital, multiplied by t and divided by n, or it is like a product r capital and dt. And this is a very useful formula for future. It is, you know how e to the power x, it is like power of exponent, can expand in the Taylor series. And yes, so if we replace x by r dt, it will be 1 plus r dt, but r dt is r little, so we have 1 plus r little. No, later we will use this formula. From this, r little equals e to the power r dt minus 1. Maybe you have any question about it? No? Okay. After that, you remember that if you put your money on the bank account, so through the time t, on the final point, we have the amount bt. Yeah, it is b0 multiplied e to the power rt. And from this formula, we can obtain r. Yes, it is first we divided both sides by b0, and after that, we find a logarithm, so we can obtain r little, like this expression. And you remember, we detailized this in the lecture 2. It was like logarithmic interest rate. And it is very interesting what will be if it is not bond or like a bank account, but if it is stocks. So if we write this formula, but instead bt write st, yeah, I understand. So like st equals s0 multiplied e to the power in no rt, okay, to the power yt. So if we find y, no, it is the similar, it is the same. Y equals this, yes. So it is like logarithmic interest rate from lecture 2. And it's very interesting in this case. It is random value, because st, it is random value too. So we can find mathematical expectation from this value and variance from this value, yeah? Because you see that this formula for interest rate, it is like ordinary formula, and bt, it is not random value, yes? But in this formula, it is a random value, so we have possibility to find the mean and variance from this value. Yeah, and you remember that for binomial model, it is like a condition for existence risk-neutral measure, and the border case, it is when d equals u and equals 1 plus r, and 1 plus r equals e to the power rt. Yes, from previous slide. And exactly today, we can give the answer on the follow questions. how we can find U and D. Yeah, you remember that when we considered the one period model and multi-period model, yes, we always said that suppose the initial price S, and at any next moment it should be only two scenario, because binomial model S multiplied U and S multiplied D. And we suppose that U and D are given. But I say to you that this U and D can be found from historical stock fluctuation. And today we are going to learn how U and D can be found from historical stocks. Okay? Is it interesting? Yes. Um, and all these three questions are connected. Okay. Um, the main assumption for this. First, the rule for constructing the binomial tree. Sorry. 1 second. Uh-huh, 1 second. Sorry. Um, sorry. Okay, about assumption. Um, assumption. You remember this rule for constructing the binomial tree. It is like the next value equals the previous multiplied to u with probability qu, or the previous value multiplied by d with probability qd, where qd, yes, it is a risk neutral measure. So, and the next assumption will be that this value log Sn minus 1 divided by Sn will be independent. And why left side equals right side? It's easy to check. If we consider the right side, this right side, and we can write this sum. So if n equals 1, it will be log S1 divided by S0, yeah? But log of ration is difference, yes, is different. So we can write this like log S1 minus log S0, okay? Yes, it is from for n equals 1. For n equals 1. For n equals 2, what we have? Yaroslav. Volodymyr. Can you hear me?
It should be log S2 minus log S1.
Yeah, thank you. Nice. Log S2 minus log S1. And we can continue this, yes? And at the end will be For n equals n capital minus 1, it will be log s n capital minus log s n capital minus 1. Oh, and what we can do in this case, you see that this log s1 with minus and with plus, yes? If we write this for n equals 3, it will be log s3 minus log s2, yeah, s2. So log s2 is crossed 2. And this log will be crossed if we consider n little like n capital minus 1. And as a result, we have just log Sn minus log S0. But difference of this logarithm, it is exactly log Sn divided by S0, okay?
Okay.
Okay, thank you. And we assume, I repeat, that all this log Sn minus 1 divided by Sn for any n are independent. In this case, we can find the mathematical expectation for this y. For this y, and what is y? Y, it is formula 2, yes? And variance. So y, according to the formula 2, it is this expression. And we can write 1 divided by t before mathematical expectation. And instead of log Sn divided by S0, write this sum. It is from previous slide, yes? Log Sn divided by S0, it is sum. It is this sum. Okay. And after that, we move mathematical expectation from this place to this place. Why it is possible? In what case mathematical expectation of sum equals this, the sum of mathematical expectation? Mikhailo, do you know?
I forgot.
Forgot. Volodymyr?
I also don't remember.
Okay, maybe someone? No? Okay, it is in case where this value are independent. So mathematical expectation of some independent random values equals sum of mathematical expectation. Only if these values are independent, but we assume, yes, that they are independent. Okay. And now we need to write, no, after sign of sum, what is mathematical expectation for this expression in the brackets? Yes. How we can find mathematical expectation in general? It is the value multiplied its probabilities. Yes. It's random value, because Sn can be or Sn minus 1 multiplied u or Sn multiplied d, yes? Because it is binomial model. So mathematical expectation equals, no, okay, I can explain in more detail. So we have Sn, and at next moment, oh, okay, Sn minus 1. At next moment, it is Sn minus 1 multiplied u, or with probability Qu, yes? Or Sn minus 1 multiplied d with probability Qd. So if we would like to compute mathematical expectation, it is this multiplied Qu and this multiplied Qu. It is if we want to find the mathematical expectation from this. But we would like to find a mathematical expectation from this, where the previous value is assumed like constant. Yes, so only this random values. So it is like Sn minus 1 multiplied to u divided by this like constant, and with probability Qu multiplied Qu plus this multiplies Qd. Okay, can you see the mistake in this?
It's for the second addition where log Sn minus 1 and u. There must be d.
D. Okay, okay. It is Mikhailo. It was Mikhailo.
Yeah, yeah.
Oh, thank you. Thank you. Yes, really. After that, we can cross this and this. So we have log uqu plus log dqd. Yes, log qd. But you see that I don't write sum. Why? Can you explain? No?
Because our addition don't
Depends.
depends with n. So
Yes.
we no need to write
Yeah, you're right. So it is like the same value plus the same value plus this, and it repeats n times. Yes, so it is just n multiplied by this expression. Okay, okay, you are right. Thank you. Okay, so we would like to find wanted to find mathematical expectation of this growth rates, and we have done it, and this answer okay. The next what we wanted was to find the variance from y. It is the same, we write the same variance. After that, 1 divided by t, we write before variance. But y square, do you remember?
The formula of var, the general.
Yeah, it is like properties, yes. For variance, it is that constant. If we find the variance of random values multiplied by constant, so we can write constant in the square, yeah, before variance.
Yes.
Yeah. Okay. Thank you. And instead this ln Sn divided by S0, we write sum. Yes, it is like in previous slide, in previous case. Yeah, and we see that again it is var ln Sn divided by Sn minus 1. Okay, and if we find this var, yes, we can find so variance of sum equals sum of variance because all these values are independent. And if we find the variance of ln, it will be the expression which doesn't depend on n. So you see that it is without sum and like at previous slide, and we only multiplied this expression by n. But after when we find variance, so the formula is sorry. The formula is that variance, for example, from x. What is formula from theory probability? It is like mathematical expectation from x square and minus, do you remember how we can enter this formula? Variance of dispersion of x, it is mathematical expectation of x square minus, do you remember?
Minus squared mathematical expectation.
Yes, nice. So mathematical expectation x square, it is like in previous slide ln u square, because we write ln s multiplied u square, no, this, and minus, and mathematical expectation x from previous slide, it's ln u qu plus ln d qd, and in the square. Okay, and after that we need to find like square from this sum. So it is first square, second square, and minus the double product this for this, yes. And after that we can write this the common factor, and in the bracket will be this expression, and this expression we can write like ln u divided by d square. So in this case the answer, we can find variance from y, and it is this. Okay, and we can notice that if t equals 1, no, 1 year, so variance we will call like volatility. And mathematical expectation we can call it like mu, and it is will be drift or trend. Okay. And now it is like a step aside, a theorem about expected returns of the stock. You remember that return on investment, it is like the final value minus initial value divided by the initial value. If you would like to find the mathematical expectation from this, yes, because Sn it is the random value, and we divided by t, no, to annualize this expression. So we can divide this by this minus this by this, and it's 1. And after that, we can write this as n divided by 0 like the product from Sn divided by Sn minus 1. And it's easy to show, and from 0, yeah, from 1 to n capital. So it is product from 1 to n capital, because it should be product, yes, product. S1 divided by S0, it is for n equals 1, multiplied for n equals 2. What it should be? It is for n equals 1, for n equals 2. Sophia. No, n equals
It will be S2 divided by S1.
yeah,
Just
and
okay.
yeah, and continue.
Multiplied by S3, multiplied
Divided by
by
S2,
S2,
and so
and
on.
so on. Mhm.
Yes. And the next Sn divided by Sn minus 1, yes? And you see that we can cross S1, S1, S2, S2, S3, S3, and yeah, Sn minus 1, Sn minus 1. And in the result, it should be only, it leaves, yes, only Sn divided by S0. So this expression. Okay. After that, the mathematical expectation of the sum, it is sum of mathematical expectation. Mathematical expectation from 1, it is just 1. And mathematical expectation from products of independent values, it is mathematical expectation. It is product of mathematical expectation. So this to the power n. And mathematical expectation, this Sn divided, no, this ratio, Sn divided by Sn minus 1 from previous slides, we know UQU plus DQD, n to the power n. So mathematical expectation, it is this to the power n. Okay. Okay, and UQU plus DQD, it is 1 plus R. 1 plus R. So 1 plus R, it is e to the power r dt and power n, yes? And dt multiplied n, it is just rt, so we have this result. So we have this result if we would like to find the annualized return. The theorem that the under the risk neutral probability under the risk neutral probability measure induced by the binomial tree model, the expected returns of the stocks is identical to that of the riskless bond, because for the riskless bond, yes, for this it was like if it is not riskless, it should be, no, for example, it is like A, no riskless, and AN divided by A0 minus 1, yes? No, this divided by this minus this divided by this, it is 1. And AN for riskless asset, you know this formula, it is for continuous interest rate. A0 multiplied e to the power RT divided by A0 and minus 1. So this, it is for riskless value, and it is for random value. And you see that the answer, the results are the same. So the expected returns of the stock is identical riskless, riskless bond. Okay, it was like notification. And we continue. So at the previous slide, at the two previous slides, we find mathematical expectation from this y and variance from this y. Yes, and we said that if t equals 1 in this formula, in this formula t, yeah, this period, if it is 1, so it would be trend or drift, and for variance it should be volatility. Okay. So what we can say, what we see, we see that from historical data, yes, if we have historical data, I mean that first we have S0, S1, it is the stock prices, and SN minus 1 and SSN. It was historical prices. After that, we can find the logarithm and differences. So we have log S1 divided by S0 log, it should be natural logarithm, S2 divided by S1 and so on, and the final log Sn divided by Sn minus 1. Okay, this series, and for this series it is it's very simple to find the mean average, and this average will be mu, and it is easy to find variance in, and this variance is sigma. So it is like estimation of mathematical expectation, and this like mathematical like estimation of variance. Yes, so it is, we can find this from historical data. Yeah, mu and sigma. No, it is for 1 year. If we have for 2 years, so it is we need to find for 1 year. And we would like to find U and D. You remember, we wanted it times year ago, some weeks ago. Okay, so we have two equations, but one unknown value, second unknown value, and third unknown variables. Yes, because QU it's 1 minus QD. Yeah, but anyway, we have three unknown variables and two equations. How we can solve this system? Yes, only if we assume something, and there are two ways for assuming. The first way is called the method of symmetric probabilities, and the second the method of symmetric limits. In the first case, we suppose that QU equals QD and equals no half. I don't like this method, to be honest, because we know that it is a risk-neutral probability. We know how to find risk-neutral probability. So more I like this method of symmetric limits. Suppose that U equals 1 divided by D, but probability we can find from risk-neutral condition. In this case, in the methods of symmetric probabilities, for example, we replace U like 1 divided by D, 1 divided by D, and we have QD like 1 minus QU, and we have only two unknown variables and two equations. And from this, we can find U, D, because D it is 1 divided by U, and we can find QU. But now we are interested exactly in this. Yes, because you remember our problem, we needed to find U and D because it is like should be given for constructing the binomial tree, okay? So, so we can use or this formula or this formula. How to solve this system with this assumption? It should be the question in your today's test. Okay. Okay. After that, we can notice that if the dt the more or less than 1, so that risk-neutral expected growth rate, mathematical expectation from y, is a function of interest rate and volatility. And it's possible to obtain this formula. So we will use this formula, but without deriving. Yeah, it is mu equals r minus sigma square divided by 2. Okay. And example, for example, the initial price from stock is 100. The volatility from historical data, it is like 10% from this, so it is 10, and interest rate is 5%. Construct a binomial tree with 20 periods to value a 3 months investment. So we have, yes, it's initial price, it is volatility, and it is 3 months, it is 1/1 of 1 year. We have 20 days, and interest rate 5%. First we can find dt like t divided by n. You remember this this formula, this assumption from the first today's slide. dt, and this dt we can write instead dt, replace dt, yes, this, and sigma we know. So in this case in this case it is formula. What is formula? No, it is like this formula, yes, this way, but I repeat, it doesn't matter. So we found u and d. So if we compare this, so it is like this, but without mu dt, yeah, because no, it should be very little variables. So we can find u and d, and after that we can get this graph. So initial price 100, and it is like binomial 3. And you see, maybe not you see, but if number of period n tends to infinity, binomial parts will look like Brownian parts. But you don't know now what is Brownian parts, so it is you need only trust. But Brownian motion we will learn in the master program. Okay, yes. So it is like binomial tree, and this it is like concrete path. Yes. Okay. Oh, this. So now we only found U and D, yes, for binomial tree from historical data. And now we know how to find trend and volatility. And the next our goal to obtain the stochastic representation for this value. For this value. It is like really a Cox-Ross Rubinstein model. It is like binomial tree, but we assume that the number of steps tends to infinity and dt tends to 0. It is, you remember, it is the value of what we today consider, yes? And we can write this like sum of independent values. We can denote these values like h sub n and up and capital. So log and so this log it is this log it is like sum of hn. Yes, this log is sum of hn. And this very important moment, we use central limited theorem, and according this limited, the sum of independent and identical distributing values, yes, for n tends to infinity, this sum is distributed under normal law. So it is normal distribution variables with mean. It is mean. You remember that the mean from this it was mu from, but mu multiplied t, and sigma square multiplied t. So this value have this distribution. Okay. And maybe this you know that if the random variable have normal distribution with these parameters, then we have find the normalized variables z, yes, and for this we from x subtract mean, yes, mean, and divided by by square root from variance. Yes? Do you know this? Did you know this before? How?
Yes, of
Yes,
course.
yes, of course. Thank you. Normalize.
From probability courses.
Oh, thank you. And after normalization, we have standard normal variables. Yes, variables. Okay. Z is we can denote like Z is standard normal variables, and from this formula you see that x minus a equals Z multiplied b, so x equals a plus Z multiplied b. So all this you know from theory of probability. Okay. If we know it was if x have a normal distribution with these parameters. If we have not x but this, and it is normal distribution with these parameters, these parameters, we just write this instead a, we write this, yes, sorry. So, yes, it is, we use this formula. X, it is log of this ratio. A, it is mu t from previous slides, plus z, it is standard normal variable, and b is, it is b, yes, it is a, so it is a plus z multiplied b. Okay, and from this formula we can find this ratio. So if it's logarithm, so Sn divided by S0 equals, what equals? If it is log sub year, no, natural logarithm. Can you say? No, I mean if log, no, ln, okay. If ln там x equals c, for example, from this x equals, how I can write, how I can find x from this. If ln x equals c, so x equals
E in the power of
c.
c.
Yeah, you're right. You're right. So in this case, x, it is this, yes, it is this, equals e to the power c. But c, it is all this, yes, to the power c. What it is c. And from this, we can write Sn equals S0 multiplied e to the power c. No, this c, mu t plus sigma square root from t and z. So we get the stochastic representations for stocks, да, for stock price. So stock price at any step n equals S0 multiplied exponent to the power mu t plus sigma square root from t multiplies z. Why it is stochastic representation? Because z, it is stochastic variables. It is which have standard normal distribution. Okay, and you see it is like a theorem. The distribution of Sn converge to the log normal distribution. that means that Sn equals S0 multiplied exponent of this. And this, instead mu, we write R minus sigma squared divided by 2. Yes, it is from today's presentation, and we assumed this without proving. Mu equals R minus sigma squared divided by 2. Okay? And it's very important because it is like model for stock prices. So we model stock prices like stochastic representation, like stochastic representation. Okay. And after that, we go on, and we need to price a European call option. And this formula will be obtained like the limited case of Cox-Ross Rubinstein model, where dt tends to 0 and the number of steps tends to infinity. Okay. Yeah, yes, we don't need to use exactly Cox-Ross-Rubinstein formula. It is like only a Cox-Ross-Rubinstein model. So we assume that it is like a binomial multi-period model. Yes, and we would like to find the fair price for, okay, and we would like to find the fair price of a European call option. So we write that fair price of European call option equals, according definition. No? You remember, according definition, what is fair price of call option? How we can say this? Volodymyr, how we can say what is the fair price of European call option? For one period model or for multi-period model, it is like in general, what we mean if we say fair price of European call option. Do you remember? No?
I can't formulate it.
No, it is like
It's
you can see on this expression. Maybe Sophia can help.
Yeah, I wanted to help, but I accidentally sent wrong reaction. There is some complicated formula about it, which I know like from formulas, but I know whether it's correct. So, is it like this Black-Scholes model? Or no, it's not it. Okay.
No, it's not it. It's not it. Okay, let's remember, if we have call option, yes, and for example, no, okay, if we have call option, and no, it can be one period model and multi-period model, and for example, we can find the Payot function, yes, Payot function. Payot function, do you remember the formula for Payot function? If we have the European option with the strike price K. Strike price. Strike price K. and там S is market price at the time of exercising. Yes. Payoff function, what is this?
It is max of st minus k 0?
Yes.
Or
Yes. We can write it's like S minus K from with plus, but it means like max, yes, max between 0 and S minus K. Yes, it is Payo function. Payo function. So at the end of period, at the time of exercises, yes, if you are holder of European call option, you can get this money S minus K, yes? This money. Okay, but now I ask you to find fair price of this call option, because if this scenario is likely for you, it is S minus K. If not, it is, yes, it is 0. So S minus K if S more than K, yes, and 0. So it is like a random variable. And what is fair price for this? First, we learned this formula for one period model, and after that we used this formula, we repeated this material when we learned about multi-period binomial tree, multi-period. For one period, for example. For one period, да? Там we know this as U, as D. We can find the risk neutral probability as U with probability QU, as D with probability as D, QD, as D with probability QD. For example, we find QU and QD, and now we need to find fair price. How we can fair price? It's like present value for this moment.
it was like, as I remember, I just a little bit forgot it, or I have to repeat it, is e in the power RT and multiplied by our EQ of the payoff function.
What is EQ?
It is like expectation we've been searching for.
Yes, you're right. For one period, was mathematical expectation, yes. With this Q, it is means that respect to risk neutral measure, and from this, from payoff function, and
Yes.
and really we need it is like present value, so we need to multiply it by a discounting factor, and it should be or 1 plus r, or we can write e to the power r. Yeah.
Okay, yeah. I remembered now. So we just did this.
Yes. So please remember this definition. What is fair price? It is like just definition. Definition is discounted mathematical expectation of payoff function under this risk neutral measure. Okay? Okay? So
Yes, okay, thank you.
yes. So welcome. In this case, fair price, yes, it is this factor, discounted factor, it is not one period model, it is multi-period model. So it will be 1 plus r to the power n, yes, and mathematical expectation from f, So this discounting factor we can write or like this, or like this, yes, and mathematical expectation from no, it is a function from market price. But now we derived the stochastic representation for this market price. But what is f? It is like s minus k if s more than k and 0 otherwise, yes. And we need to find the mathematical expectation from for this value. But in the continuous case, how we can find mathematical expectation? Because for the discrete case, it is like sum of products, yes, value by its probability plus value by probabilities. How we can define the mathematical expectation in continuous case? Do you remember? Michailo, do you remember? From theory of probability, mathematical expectation for
It
continuous.
is integral.
Yes.
To find the integral.
Yes, it is.
And it is the integral from k to infinity, s minus k, and
So, no, for example, mathematical expectation from x, yes,
okay.
it is integral with minus infinity to plus infinity, yes. And what is this? Under integral? Sophia, do you remember?
Yeah, 1 second.
Maybe Volodymyr?
I can't remember this formula.
But you already studied this formula?
Yes.
Yes? Okay, only don't remember, yes? Doesn't remember. Yeah, you don't remember. Okay, but Sophia?
Yeah, let me get it so I can get it correct. It is f x, and fx is some density function, probability density function of this, as far as I remember.
Just f with x dx?
And so
No,
what?
it's multiplied by x.
Yeah, yes.
Yeah. Thank you, Yaroslav. Yes, really, it is formula from theory of probability, mathematical expectation for continuous variable. It's integral from minus to plus infinity, and x multiplies f from x. Yes, and it is the density of distribution function. Yes, density of distribution function. So in our case, so instead mathematical expectation we write integral. X, it is this our value. It is this our value, and this value will be not 0 when s more than k. Yes. So instead integral from minus to plus, we write integral from some value to plus, and this some value, it is exactly when s more than k. S more than k. So we need to find this value like the solution when s more than k. Okay, So mathematical expectation integral after under integral we write x. It is this value s minus k. Instead s we write stochastic representation and this k. Yes, so it is our x. And multiplied the probability density for k for x, but in x this stochastic variables, and we proved according stochastic according central limited theorem that it is a normal distribution, and the density it is e to the power for standard variable e to the power minus z squared divided by 2 square root from 2p and dz. Okay. After
Sorry, sorry. So the probability function is what you have just said for our call option. It is e in the power minus, this.
yes, it is
Okay.
it is formula for normal distribution, probability function for normal distribution. Yes, for this z, because all rest it is constant. Only z is stochastic variables, random variables. After that, we can write this integral of this sum, of this difference, yes, this minus k, like the sum of two integrals. It is first minus, it is second integral, and in the first integral, this is this you see, and this e to the power minus rt we can write under integral. Yes, it is this, it is clearer. It is this, this we write, and e to the power minus z squared divided by 2. Yes, so we have this e to the power multiplied e to the power multiplied e to the power, so we can write this like e to the power, and all this it is sum, yes, minus rt plus z sigma square root from t plus rt and minus sigma square multiplied t divided by 2 and minus z square divided by 2. Yes, so you see this crossed, and this we can write like minus, and in the bracket will be maybe I can write this 2 and this multiplied 2. So it will be z square. Yes, it is this z square. After that, minus 2 z sigma square, yes, only sigma square root from t and plus sigma square, and no sigma sigma, yes, sigma square, and t, no, t, okay, and t. And you see, what is this in the bracket? Z square minus double product z by sigma square root from t plus z square sigma square square root from t. What is this?
So it is z minus z. Yeah, it is squared formula, but I'm kind of.
Z, yes, it is like a double product z by sigma
Sigma
square root from t. Yes,
square
yes.
root t, yeah.
Nice, nice, nice. Yes, yes, really, it is z square minus 2. Yes, okay. And this expression we can denote like u, like u. Okay. So, like u, this, yes. So du, dz, it is like changing of variable, да? Yes. And d1 like, no, if we change the variable, this, yes, so it will be s1 divided, 1 divided by square root from 2p e to the power minus u square divided by 2 du. And the second integral we rewrite without any changing. And you see that this, it is the probability, integral probability function from d1, and this is probability function from d2. Yes, standard probability integral function. So we have the formula for call European option, but we don't know how to compute D1 and D2. Yeah, because you remember it is D1, it is when your function s minus k, s will be more than k. Yes, it is s. So for this we need to solve the equation where Sn equals k, and after that we can get this value for z, what is equals to 2. No, we can find a logarithm, and from this find this z d2, and it is exactly we obtained the celebrated Black-Scholes formula for fair price of European call option. It is very simple, where it is like integral normal distribution function, and d1 and d2 we can compute from this. It is it is Merton, Black-Scholes Merton. After that, it is easy to write put call parity, and we need to notice that this model, like stochastic representation, not a good approximation to security prices. Everybody knows this, but this formula is very useful, like the first approximation. And yes, you see that this formula is the most important and famous formula in all of finance and economics. Yes. The assumption we can read by yourself, because there is end of a lecture. The assumption on the market, And how we can use this formula? We can compute first D1, D2, after that to find this integral function from this. It is, no, there are a lot of ways, and substitute in this formula. But beside this, we can, the formula in Python, it is from Mibian, and I will show this on the lecture. Okay? So I finished in time. Do you have any question? Artem,
No.
Sophia, Volodymyr?
No questions.
No question.
No.
Okay, so we will meet at 3 p.m.
Okay.
See you.
Okay, in 3 minutes.
In 3. Ah, in
Okay.
3 minutes. Oh, okay, okay. So
Maybe 10?
maybe да, maybe 3 and 3 p.m. and 10 minutes. Okay, 10 minutes.
Okay.
Thank you. Thank you.
See you.
See you.